Hello YouTube. It occurred to me that at some point somebody's going to probably eventually ask me if I have a schematic drawing of the ALU project that I've been working on. And I don't have a schematic, but I have created this wiring diagram. So I thought I would put together this video where I'll go through this wiring diagram component by component, step by step, so I can explain, how somebody else could build this if they wanted to. So let's go ahead and get started. So this would be the very first thing you want to do, is just lay out your breadboards, and I'm using 3, and I think that's what you need. I don't really think you could build this up on just 2 breadboards. I think it would be too tight. It'd probably be impossible, and if it were possible, it just wouldn't look very good. The wiring does get very tight around the ALU, so this is kind of our starting point. And I'm just laying out the major components onto the breadboards. And this layout that I'm using, it's not arbitrary. Like you can see, I've got the dip switches lying exactly in line below the LEDs on this side. I've got the dip switches on this side exactly below the LEDs on here. And we have our inputs down here on the bottom, we have our processing happening here, and we have our outputs here on top. So I think this makes logical sense. If you want to experiment, of course, go right ahead, but just know that there was some thought that went into this layout. It's not, like I said, it's not arbitrary. So the next thing we'll do is we'll hook up power and ground to our various components. I will mention that this hex inverter 7404 and the 7402 NOR gate that I'm using, these are technically optional. We'll talk more about those later. Here I'm just putting power to the ALUs and ground, and then down here where I'm just running power to the different dip switches. This push button latch, I have found that not all push button latches have the same internal wiring. So even though they look identical, the push button latches look identical, I've found that just the way that the different pins are connected internally isn't the same. So before, if you are using a push button latch, and certainly if you're using something else like a slider switch, check the continuity between all the pins to make sure that you know how everything is connected before you just hook everything up as I've done here. Because I do have a set of latches that I've set completely aside because they have a completely different internal connections between pins than these latches. This latch style is the one I like, and I never would have bought the other ones if I realized they were different. But anyway, you get the point. So moving on, the next thing I'm doing is I'm hooking up a whole bunch of resistors rather. And in my build, I'm actually using resistor networks. And if you have resistor networks, I would recommend that. The only reason I'm not showing resistor networks on these slides is this program I'm using, Fritzing, and I'll try to remember to put a link to that in the description. I couldn't find any resistor networks of the appropriate sizes, so I just used regular resistors. But if you have resistor networks, I recommend using them. It'll simplify hooking up the resistors a lot. But the values here are 100 ohms for going between the dip switches and ground, and this is just the pull down resistor concept. The resistor values that I'm using for my bar graph LEDs is 220 ohms, and I find that works well, gives me good brightness without making everything blindingly bright, and vice versa, they're not too dim. But the resistor values are a bit flexible, so if you're using super bright LEDs and you find that 220 ohms is not enough, you might try increasing that to 330 or something else to get the brightness where you want, and vice versa. If you have really dim LEDs, you may want to decrease this value. And again, I'm using bar graph LEDs. I think it just makes everything easier. I just plug in the bar graph as one piece onto the breadboard rather than messing with 8 individual LEDs here, here, and here. Moving on to the next step, I'm just bridging the connection between the dip switches and the bar graph LEDs, and I'm doing that on this side and on this side. Here in this step, I'm just hooking up some output LEDs to the latch so I can tell which mode I'm in. And pay attention to this part of the video, and I'll go backwards for just a moment. Oops, that's forwards. So this is backwards. So this is what it looked like before I hooked up those LEDs. That's after. That's before. And that's after. And again, I'm just using 220 ohms for current limiting on these LEDs, but you may have to experiment with that value. And regarding the latch, I like to make it so that when the latch is down, I'm in logic mode low, and when the latch is up, I'm in logic mode high. That just makes logical sense. High is up and down is low. This would be a really good part to stop building and hook up power to your breadboard and go through and test everything. Now you'll notice I haven't ran power connections between my breadboards in this Fritzing diagram, but I'll leave it up to you to run power however you want to do that between your different breadboards. I usually just go from ground to ground and then connect the ground to ground and so on, but I'll leave it up to you to decide how you want to power your board. But once you're at this step and you have everything powered up, just slide all your dip switches back and forth and make sure that each individual corresponding LED is going on in turn with your different slider switches, and do that on both sides. And then toggle your latch up and down to make sure the LED is going back and forth. And the reason I mention taking a moment here to do that is I found when I built this project, the B side of my build, which is the right side, one of the slider switches on the dip switch bank was bad. And when I would slide it forward, I would see the corresponding LED come on. But as soon as I would let go of pressure, that corresponding LED would go off. There was something wrong with the spring or the mechanical mechanism inside. So this is just a good time to squash those kinds of bugs. If you have any issues with your dip switches, replace it now so you don't have to mess with that later. There are no output LEDs hooked up to the 4 function select dip switches. You could do that. There is room here to hook up 4 more LEDs. I just haven't done that on mine. But this would be a good time to test that as well. Just at least hook up 1 temporary LED and check that switch, and then move it over and check that switch, and so on. Or if you want to have 4 more LEDs, you can hook up 4 more LEDs for your function select here. Like I said, on mine, I just didn't do that. Okay, so moving on. The next thing we're going to do is we're going to hook up the carry output of the right side ALU to the carry input of the left side ALU. This is pin 16, it's called CN+4, so that's being just connected directly to pin 7 on the other ALU. And that's assuming that we're making the right side ALU our lower 4 bits and the left side ALU as our upper 4 bits. It makes sense to me to do that because generally our least significant bit is on the right, and as we go towards the left, our bits go up by a power of 2. So that being the case, having the lower 4 bits on the right, upper 4 bits on the left makes sense. So the next thing we're going to do is I'm going to hook up the latch to pin 8 for the mode select. So coming out of the latch, going into the ALU pin 8, and then I'm also bridging pin 8 of this ALU to pin 8 of this ALU so that when I select the mode, it applies to both ALUs. And we'll go through these next few slides quite quickly. We're just going to hook up our function select to the ALU. So the least significant bit is going into pin 6, which is S0. The next bit is going to pin 5 or S1. The next bit is going to pin 4 or S2. And the last bit is going to pin 3 or S3. And then we're just going to do the same thing for the other ALU because we need our function select to apply to both chips. So again, starting with the least significant bit, we're going to pin 6, pin 5, pin 4, and pin 3. And the next thing we're going to hook up is our operand inputs, and we're going to start with the A side. So the least significant bit is going to pin 2, which is A0, and we'll go through these quickly. The next bit is going to pin 23 or A1. The next bit is going to pin 21 or A2, and I do want to stop for a second and point out that you are skipping a pin. You're going from pin 23 to pin 21. So if you go pin 23 and pin 22, you're going to have problems. So just remember, you're going from pin 23 to pin 21. And likewise for the last bit, we're going from pin 21 to pin 19. So we're skipping over a bit. And then we're going to hook up the operand inputs to the second ALU, starting with this bit. We're going into pin 2 for A0, which I suppose at this point would actually be A4, but on the data sheet it's going to be A0. So we're going A0, then we're going to go to A1, which is pin 23, A2, which is pin 21, and finally A3, which is pin 19. And then we're going to do the same thing for this side, the B side, so we'll go through this quickly. I will say that when I'm hooking up the right side, I start with the least significant bit and I work my way up because we're going right to left. For this side, we're going to go the other way. Since the most significant bit is more accessible, we're going to go left to right. So we're going to actually work most significant bit down. So starting with the most significant bit, we're going to the second ALU, and we're going to start with pin, what is this, pin 19, no, pin 18 for B3. And then we're going to pin 20 for B2. And then we're going to pin 22 for B1. And then finally we're going all the way over to pin 1 for B0. And then we're going to do the same thing for the lower 4 bits. Starting way up here, pin 18 for B3, pin 20 for B2, pin 22 for B1, and finally pin 1 for B0. And that has all of our operand inputs hooked up. Okay, so now we're going to hook up the outputs. Starting with the least significant bit, we're going to pin 9. And this is our F0 output. And then we're going to pin 10 for our F1, pin 11 for our F2, and then finally pin 13, which is on the other side of the chip, for F3. And that takes care of the lower 4 bits. Then we're going to do the same thing for the upper 4 bits, starting with pin 9, going to pin 10, going to pin 11, and going around to the other side for pin 13. And that's all of our output LEDs hooked up. The next thing we're going to do is hook up our carry output. So remember that the carry output of the first LED was wrapped around and hooked up to the carry input of the first, I think I said LED, I meant to say ALU. The carry output of the first ALU was hooked up to the carry input of the second ALU. We don't have a third ALU. So instead of hooking up the carry out to another carry in, we're just going to hook up the carry out to an output LED, indicating, you know, when we have more than 8 bits worth of information. When you're using positive high inputs and outputs as opposed to reverse logic, the carry out is inverted. So if you hook up pin 16 directly to the LED, it's going to be opposite of what you want. If you're okay with that, that's fine, you can do that. I don't like that, so I'm going to go through an inverter, and that's where the 74LS181 finally comes into play. So I'm coming out of pin 16, the carry output, into pin 1, but really just any of the inputs would be fine. You could even go to the other side if it makes your wiring more convenient. But we're just going to go through the inverter, out of the inverter into the LED, and then out of the LED through current limiting resistor to ground. And again, that's just so that the LED will be lit up when the carry out is on, as opposed to, you know, backwards. The next thing I'm going to do is hook up our A equals B outputs to an LED. Now I want to point out that I did this incorrectly. Well, it's not that it's incorrect, it's just that the way I did it in my other video, I introduced more complicated wiring, and I introduced an AND gate, and none of that was necessary, as it turns out. I think Steve was the guy that pointed it out in my video, where if I did my wiring a little bit differently, I wouldn't need the AND gate, and that was a great suggestion. It really simplified the wiring, and it got rid of that extra gate. So what you want to do is run the A equals B line, which is pin 14, on both ALUs to some part of your breadboard, where you're not going to interfere with other things. And then I'm just bridging those connections together, like you see here, or of course you could just run this line to here, however you want to do it. And then I'm coming out of those bridged connections into another part of the breadboard, and I'm running through a current through this resistor, a pull-up resistor to high to VCC. In my other video, I mentioned I was using a 680 ohm resistor. In this case, I'm only using 220 ohm because I found that since I'm not going through an AND gate anymore, if I'm using 680 ohm, the LED is just really, really dim. So I swapped out the 680 ohm for just a regular 220 ohm resistor for my pull-up resistor, and do notice that this is going to VCC, it's not going to ground. So that's the pull-up resistor, and then on this other part we're just going through our LED to ground like normal. So this will be for our A equals B output, and again, this is when the chip is in subtract mode, and I talked all about that in the previous video that I made. So moving on to the next step, after the A equals B is hooked up, we're going to hook up this first LED, which is going to be our A is greater than B LED, and this is where the NOR gate comes into play. And if you're not wanting to hook up these extra comparator things, then of course you can tune out of all this part. But the way this gets wired is, you'll notice the carryout line coming out of pin 16 of the second ALU. I'm just bridging into that connection right here at this point, and I'm just tracing that around, and I'm making that the first input of my NOR gate. And I guess I kind of want to point out the wiring of NOR gates is a bit different than it is for AND gates and other chips that I'm used to, like OR gates. For AND gates, it's input, input, output. For OR gates, it's input, input, output. But for whatever reason, NOR is the other way around. It goes output, input, input. So just bear that in mind when you're wiring this. So we're, again, just coming straight off the carry out, making that the first input of the NOR gate. And then our second input, you'll notice, is just coming straight out from the A equals B. So the A equals B is our second input. And then finally our output is going straight to the LED and going to ground. And I found in my case I didn't need a current limiting resistor. In fact, when I put one in line with the LED, in my case it made the LED really dim, so I just skipped it altogether. Your case may be different. If you have super bright LEDs, of course, consider putting a current limiting resistor in line with that LED. The next thing we're going to do is hook up the A less than B LED, and the first input is going to be the inverted version of our carryout. So previously we bridged directly into the carryout to make that the first input of our NOR gate. In this case, we're using the inverted version of that carryout signal as our first input. And then our second input, it's still just going to be this A equals B line. If you follow the wiring around, you'll notice that it connects from here. And if you go straight up, we're just bridging directly in from that A equals B. I think I said input, but I meant to say output. We're bridging directly into that A equals B output as our second input to the NOR gate, and then finally the output is just going to that LED. And then the last thing I want to mention, labeling. If you want, you can put some labels down to make labeling nice, but more importantly, I want to draw your attention down here to this part. So let me just back up the slide, paying attention just to this part. So this is pin 7 of the ALU, and this determines if you're going to have that carry in bit be high or low. And if we're using high logic or positive logic or normal logic, where high is high and low is low instead of inverted logic, then this pin 7 behaves backwards. You can think of this pin 7 as being CN with a line over top of it. So that means by tying it to 5 VCC or 5 volts, we're actually making this low. You could, if you want, and I did this at first, instead of tying this connection directly to 5 volts, I just left a loop over wire so that I could go back and forth easily between ground and 5 volts and experiment with the 2 different modes. And if you really wanted to, you could even run down and go through a whole latch mechanism like I've done here. There may be room for that over here on this part of the breadboard. But after experimenting with the various ways of handling the carry-in on the first ALU, I like having it tied to VCC. So that's just something I'll mention. You may want to experiment around with that. So that's everything. That's the wiring complete. And hopefully you found this video interesting. Hopefully I didn't make any mistakes in the wiring diagram. But if I did, please point it out below and I'll try to update the slides. I'll put all these slides into a zip file and I'll make them available. So if you look in the video description, you can download all these pictures and you can scroll through them on your own. Thank you, and I'll see you in the next video.